Hey, sir.
How's it going?
You all right? I had a question for you about one of the homeworks.
Okay, go for it. I was just sending an email. That's why I looked a bit distracted.
Okay. Let me see which one. On a question concerning elastic collision, how do you, I guess, how do you determine the directions that the objects will go after they collide?
So the main thing is they will definitely stick together. That's the definition of an elastic collision. So it becomes M1 V1
I think that's
vector.
inelastic, isn't it?
Oh, I thought you did say inelastic. I'm sorry. Yeah, with elastic collision, if it's one dimensional, meaning a head-on collision, there's very
Yeah.
distinct ways, and we've worked out. I derived the actual formulas for you on those. And basically, either what happens is one stops and comes to a rest, the other one goes on the way the original one was going. Another option is that one slows down and the other one goes the other direction. Was one of them at rest initially, or both of them moving?
Yeah, the second one was at rest.
Okay, so yeah, that's all those equations I derived for you. You don't, we've actually worked it out where you don't even, assuming it's one dimensional, you don't even have to worry about the details. You just do those calculations that I told you turned out like the Atwood machine results.
I haven't gotten around to watching your video on the Atwood machine, or I think that's the you're talking about the one with the two wheels, right?
Oh, yeah, the Atwood machine. Well, I'm talking about the original Atwood machine where we found that the actual acceleration was big M minus small m over big M plus small m times g. Well, when we derived elastic collision in one dimension where one was sitting still, we got these neat little results that look like that. Like the velocity of the first one after the collision was m1 minus m2 over m1 plus m2. And the tension in the Atwood machine was 2m1 m2 over m1 plus m2 times g. Well, you get a result like that for one of the final velocities, 2m1 m2 over m1 plus m2. That Atwood machine was covered a long time ago when we first did kinematic, or excuse me, when we first did dynamics, Newton's second law. So that's what I was trying to use to just jog your memory. I can tell you exactly what day
Okay.
we covered this, though. Let me pull that up real quick. It won't take but a second.
You wouldn't need to tell me the day, but that formula would be useful. What was it? It was big M minus small m over the masses summed, and then something else.
Yeah, big M. It was like big M minus small m over the masses sum times g. That was the acceleration. Excuse me. Yeah, the acceleration of the Atwood machine, and then the tension in the Atwood machine was 2 times the product of the masses divided by the sum of the masses. So I'm looking.
I was talking about like two pucks, like ice pucks, hitting each other.
Yep. Yeah. So the one-dimensional head-on collisions were chapter 9. The next to the last day, the same day I did the AR-15 calculations.
That's
So if you
weird.
want
I was there for that. I'm pretty sure I have those notes written down somewhere.
yeah, what we found was VB prime was
Oh,
equal to.
okay. I do have these all written down. There's like a whole half page of it. Okay.
So this was unequal masses, elastic collision, head-on, one at rest. VB prime was 2MA over MA plus MB times VA, which looked just like Atwood's machine, except one mass and G was off. And the VA prime, that was the velocity of the initial moving object after the collision, was the difference in the masses divided by the sum of the masses times the initial VA velocity. So yeah, that was the results that you should be using for that elastic collision. And you don't even have to derive it. That was sort of the whole point of us doing that for you is when you get into 2 dimensions, all bets are off. There's some tricks to play, and I showed you those tricks, but other than that, it's pretty, it can be brutal trying to solve those equations.
Yeah, I had forgotten about these notes, and I ended up finding some help online. But like, because I was looking in the what was it? I was looking in the e-text too, and it helped a little bit, but it didn't. I couldn't quite find the same example.
Yeah,
I think
if
the
you're doing
closest thing I
chapter
saw
10,
was like it was like two particles, but I couldn't quite understand what it was getting at.
gotcha. If you're talking about chapter 10 problems, that's because they're expecting you to use momentum, which came from chapter 9. So that's probably why you didn't run across it.
Hmm.
There's an attacker
Those
sneaking up behind you.
equations, huh?
There's an attacker sneaking up behind you. I just saw a shadow.
Oh yeah, no, that's the my roommate's uh bedroom doors, like they're right next to one another.
Okay, so
Um, but these equations were, like you said, that we can use these, right?
yeah,
Like for an exam or something. Were these in the book anywhere, or was this just
yeah, they
you
were
kind
in
of helping
chapter
us out?
9. They were in chapter 9, and I thought he numbered all of them, but I definitely allow you to use them. So
Yeah, I have some, I have equation 1, 2, 3, 4, whatever. But I guess I just didn't write down which situations they apply to. Guess I wasn't thinking or something.
yeah,
What do you know what the name of the video was? Like, you upload these on
yeah,
YouTube?
it was one of the ones that had the AR-15 calculations. So there's like 3 of them, and I did the same thing in all 3. So
Okay, so just YouTube channel AR-15 question.
yeah, on my channel, of course. My
Yeah.
channel now has
Okay.
the URL of Billy, capital B, Billy, capital Y, Younger, capital P,
Billy
physics.
Younger Physics Solutions.
Yeah. So anybody else have any questions? All
Yeah,
right. Well,
I got one more, but I'll
go
hold it to
for
the
it.
end of the class.
Okay, no problem. Well, we've got one more type of problem that I want to make sure I solve for you guys. I've done moments of inertia using the parallel axis theorem. I've done moments of inertia using the integral methods. In fact, I did 3 different ones to that. I did a thin rod about its end, a thin rod about its center. I did a cylinder. And of course, there's many other ones you can do. You can do a cylinder with a hole in the middle. In other words, this cylindrical shell, if you will, or a cylindrical tube. There's all sorts of things you can do. I can actually add, even for the rod, if you want to model that rod more like a baseball bat, you might make a function of density per unit length as a function of X that is about the same on the handle. Maybe you could even include the little nub at the end. So there'd be an increase and then a small decrease, and then it would slowly increase to the diameter at the sweet spot. And then at that point, it would stay roughly constant until you got the end where there's a scoop out or whatever. So you can even do little things like that by making piecewise mass per unit length as a function. So, lambda of X. You can do stuff like that. We did introduce the concept of angular kinetic energy, 1/2 I omega squared, so that now when an object is moving, it has a kinetic energy associated with its center of mass moving at a velocity v, but it's also got a moment of inertia, or excuse me, a kinetic energy associated with it rotating about some particular point, and that's 1/2 I omega squared. So we did that. We solved the complex Atwood machine, which was quite time consuming. It took a fairly long derivation, but you ended up solving for 5 variables that were, pretty big. I mean, that's a big deal to be able to get all those variables in a closed form. And I left it in terms of just plain I, so that you can plug in, 1/2 mr squared if your 2 things are cylinders. You can plug out 1/2 mr squared for each of the 2 pulleys, all sorts of cool stuff like that. So now what I want to do is I want to, the last thing I did was an inclined plane where we allowed a can of soup, a can of actually specifically like cheese soup or cheese dip, something thick and gelatinous, if you will, that would stick to the walls really well. We allowed one to slide down an incline without friction, and then we allowed another one to roll down an incline without slipping. And we discovered that the one sliding down without friction actually was faster. In fact, it was a difference of the square root of 2 versus the square root of 4/3. So now what I want to do is I want to solve a problem. And I specifically do this because when I took this course, there wasn't a single example where anybody had worked during that. And at one time I was writing a solutions manual for another textbook of this level. And that was one of the problems. I was like, oh, wow, this is really cool. I never solved one like this. So I just don't want you guys to be like I was, where I'd never solved one. And it's a little scary the first time you solve a problem. I got it right the first time, so that made me feel good. But anyways, I'm going to make sure you see one like that. And that is, what is the minimum coefficient of friction required to allow in this case, I'm going to work a cylinder sliding down an inclined plane of angle theta. What minimum coefficient of friction must exist so that you can have it roll without slipping? So let's get started on that problem. When that's done, we're going to jump right into chapter 36. So this is example 1. And today's date is 10/29/21, and this is P241D01B. And I think this black pen's about to die, so I've got to keep an eye on that. Let me turn on my document cam because y'all don't want to look at my liver spotted forehead. I look like Jimmy Carter a little bit. All right. Anyways, here we go. So what we're imagining, and remember, I've already verbalized the question for you, is what is the minimum coefficient of static friction required to allow a cylinder, like a can of soup, if you will, to roll down a can of cheese soup, that is something sticky, to roll down an incline without slipping. So here's our incline. I'm going to draw this part really small because the free body diagram is really the part that needs to be big and matters. We're going to assume the incline is an angle theta. We're going to assume the cylinder has a mass m, a radius r, and therefore a moment of inertia equal to 1/2 mr squared. Okay. And the reason why I did a can of cheese dip is because if this was like chicken noodle, you could imagine as soon as this thing starts to try to roll, there's no impetus to make it roll because the liquid's perfectly happy sitting perfectly still inside of there. So it's going to stay still while the metal can around it rolls a little bit. But if you use something like, a can of mashed potatoes, if such a thing existed, or a can of cheese dip, then obviously it wouldn't. Okay. So let's draw a free body diagram. And that looks like this. So here's our object of mass m, radius r. And I'm going to draw my inclined plane. I'm going to try to draw it at the same angle I had, but it's not necessarily going to work out that well. There's my y prime axis. This is going to be my x prime axis. This is my negative x prime axis. This is my negative y prime axis. And let's go ahead and assume that marker is crap to bed because it's not doing very well. So this has a mass m, so the forces acting on it are the object's weight, which is going to be m times g. That's going to point vertically downward, which isn't aligned with any coordinate system, right? So that's why I just drew it as a black vector. Now, we're also going to have a normal force that is, in fact, parallel to the y prime axis. So that's going to be F normal. And we also have a friction force that's going to be in the negative x prime direction. Notice in order to make the ball rotate this way, the friction force must act on the ball in this direction. So that's our friction force, which we're going to just go ahead and say is mu times F normal. Okay, so the friction force is acting that way. Now what we can do is we can convert mg. If we notice this right here, this is the angle theta. Therefore, this angle right here is the angle 90 minus theta. So this angle is theta. Now, normally, and I really should have, to be honest with you, normally I attach this mg to the center of mass, and that really should be where it's attached. But you can see I can just slide that along. And we know for a fact that's where it's attached, by the way. I can just slide that along and this angle doesn't change. So the key point is I drew it here because I've noticed students are having a harder time seeing this angle theta is here when I have it attached up here. But that's really the case, is mg is actually acting right here. So that's going to come in handy in a second. Okay, so now I can break this component up into one in the negative y hat or y prime direction. That's going to be mg cosine theta. And then I have mg in the x prime direction. Its component is going to be mg sine of theta. So remember that mg is actually acting right here, even though I drew it over here. I just this time did it for clarity of the symbol, because when I did it right here, it was a little less obvious to students that that angle was theta. So now we're ready to roll. What I'm going to do is I'm going to write Newton's second law. The summation forces in the y prime direction is equal to mass times acceleration in the y prime direction. We're not expecting this ball to bounce up and down or do any kind of crazy accelerations in the y direction. So we expect the acceleration to be 0. So in this case, all we get is F normal, which is in the positive direction, minus mg cosine theta is equal to 0. So that tells us, in fact, that F normal is equal to mg cosine theta. So I'll call that equation 1 just for the heck of it. Now I'm going to do the summation forces in the x prime direction is equal to mass times acceleration in the x prime direction. Now in this case, I've got mg sine theta acting in the positive x prime direction, and I've got F acting in the negative direction. So I'll just say mg sine theta minus F is equal to ma. That's going to be equation 2. Okay. Now I've got the Newton's second law for rotation, and that's the summation of the torques is equal to I times alpha. Okay. Well, in this case, what you're going to see is this thing is rotating about the center of mass of the cylinder, the symmetry axis of the cylinder of the can of soup, right? This mass, and here's where I told you mg is actually acting here. Okay. This mg is acting right through that center of mass. Therefore, it has 0 lever arm. Therefore, it causes 0 torque. Similarly, the normal force acts along the line that goes from the contact point through the center of mass. So it too is going to have no lever arm. So the torque for that is 0. In fact, the only torque we get is this torque, which causes a rotation this way, which happens to be in the same direction as the positive acceleration in the x direction that I talked about. So that's a good thing. In other words, I don't have to mess with signs and crazy stuff like that. So for that one, we see this F is perpendicular to its little r vector. So its lever arm is in fact the radius, and that radius is in fact perpendicular to this. So we already have F perpendicular times r. So all I have to write is F times R, that's the torque, and that's equal to I, but I, remember, is 1/2 mr squared times alpha. Okay. Now what you can see is that I've got 2 r's here. One of those is going to cancel out, leaving 1 with this one. Now I've got r times alpha, and rolling without slipping, I'll write over here.
Wait, what got subbed in at that last equation there?
I, which is 1/2 mr squared.
Okay. All right.
Okay. Now, rolling without slipping means that the distance it travels along here has to be equal to the arc length that it travels along here, and that has to be equal to the radius times the change in angle. In other words, S is equal to R times theta. If you take the first derivative of that, you get V is equal to R times omega. Well, in this case, it happens to be big R. And if you take the derivative of that, it happens to be A is equal to big R times alpha. So you see right here, this is A. So I'm trying to solve for friction and then ultimately for the coefficient of friction, mu. So remember, I'm really wanting mu, but I'm going to also get A as well. Okay. I'm also going to get Fn, which you see we already did. Okay. So we've already got the Fn part from equation 1. All right, so now we're going to carry on our work. And what I'm going to do is rewrite equation, well, it's going to become equation 3. I'm going to rewrite it. It's now F is equal to
1/2 MA. Okay, that's going to be equation 3. Now, using it this way, this is going to eliminate F, which is really the first thing I really wanted, but that's okay. If I solve for A, I could eliminate A and then get F as my first thing and solve for mu, but I don't care. I really just want to make sure I get all of them, even though this was the main goal that I was shooting for, but it's kind of nice anyway. So I'm going to take this F and plug it into equation 2. So I want to do 3 into 2, and that's going to give me, in fact, mg sine theta minus 1/2 MA is equal to MA. You can see that is going to cause us to have, for starters, you can factor out all those M's. So that's nice. We're getting an A that's going to be independent of the mass. So factoring out all those M's, I can now say, when I pull this 1/2 A over here, this is going to become 3/2 A. So you can say G sine theta equals 3/2 A, or A is equal to 2/3 G sine theta. So now we know the actual acceleration of the cylinder down the incline. Okay. And it is a constant, because notice the incline is a plane tilted at a constant angle theta. So this is a constant. So we can still use x equals 1/2 AT squared, V0t plus V0t plus x0. We can still use V squared equals V0 squared plus 2a parentheses x minus x0. All those kinematic equations that we found for constant acceleration, they fit this. So even though we've added this complexity of having a thing rotating in addition to its center of mass moving, still gives us a nice constant acceleration down an incline. So now I've gotten A. That was just a lucky happenstance. But now I can take that and plug that back into, let's say, equation 3. So let's plug, make sure you can still see that. Yeah, plug A into 3. So now we know the friction force, which is 1/2 the mass times the acceleration, and the acceleration is 2/3 G sine theta. We can see we're going to get 1/3 mg sine theta is how big the friction force has to be. Now we're going to use F is equal to mu times the normal force. In doing that, I'm going to say mu times the normal force, which from equation 1 was mg cosine theta, is equal to 1/3 mg sine theta. Now you can see that the mg cancels out on both sides. And I want to ask you a slightly more important question. What exactly is this type of friction coefficient? Is this static or kinetic friction?
That'd be static, I think.
Exactly, because kinetic friction would mean the surface of the ball is moving at a rate relative to the surface of the plane. And that's the very definition of slipping, right? So since this is rolling without slipping, it has to be static. So I just want to make sure you guys remember that. So obviously, to solve for mu, I'm just going to divide by cosine theta. So I get mu has got to be equal to 1/3 tangent of the angle. So that's a nice result. That just tells us, hey, if we really want rolling without slipping, we got to make sure the angle isn't bigger than or the tangent of the angle isn't bigger than 3 times the coefficient of static friction. If it is, then we're going to get some slipping initially. Any questions on that? I'll go ahead and circle this other answer, and actually I'll circle these in a different color so they'll stand out a little bit. So no questions on that? Actually, this one was already green, so. All right. Well, that really is all you need for chapter 10. Like I said, you had all the concepts for chapter 10
obviously the homework was due Wednesday, and I told you you had plenty of material by that time anyways. But you also had plenty of exercises even before today, but I wanted to put one of these in there just so you'd have that experience under your belt as well. So you certainly can finish the homework that's due Sunday on chapter 10. So that's a reminder. Don't forget to do the homework on Sunday or by Sunday. So does anybody have any questions on this or any other chapter 10 material? Because we're getting ready to move on to special relativity. So this is special relativity. So I wanted to talk to you a little bit first about letting you know what the word special means. Okay. Like I've heard elderly people, for instance, say, "This is my special friend," which is sweet, kind of in an old person kind of way. You know, they're trying to say, "Hey, this is my," or they'll say, "my lady friend." I always took it as them trying to say, I don't want to be overcommitting her to saying that she's my girlfriend. But it meant special as in really, really important to them and that sort of thing, and really, really useful. The special and special relativity is a quite different version of special. Okay. Special in this context means more like specialized, are only valid in a special circumstance. So that's what they mean by special relativity. And I'm going to explain what Einstein did, but I want to first give you a little bit of the history. So this basically special relativity paper was written in 1905. And in that year, Einstein wrote, think about 7 papers, just about every one of which could have won the Nobel Prize. Special relativity is the one that did not win him the Nobel Prize, in fact, people were still a little in 1906 and 1907. But his photoelectric effect, which was the creation, one of the creating papers of quantum mechanics, which he denied was right until the day of his death, that was the one he won the Nobel Prize for. And so cocky was he and his former wife about it, or at that time it was still a wife, that he guaranteed, since he had no money right then, that he would give her his entire Nobel Prize money if she would allow him to just divorce without leaving her anything else. And she took the deal and of course got the money. So that gives you some idea of how cocky he was about it. But it was a really beautiful year. And Einstein really was a upper level of genius. Basically Einstein, Darwin, Aristotle, Newton, and maybe not even Aristotle. It's hard to tell because of time lag. But here's what's going on. So in the early 1900s is when Einstein's studying Maxwell's equations, and he's studying them not necessarily as experimentalists, even though he was actually really proficient with mechanical things. He built, his family was a family of people that repaired and worked on refrigerators and clocks and stuff like that. So they were a mechanical group, and as was he. But he was also brilliant with his imagination in terms of mathematics, as well as in terms of geometry and rendering things in 3 dimensions and stuff like that. And he took Maxwell's equations of electricity and magnetism and really committed himself as a genius in that category. And what I mean by that is a lot of people have said a genius is the person that can hit a target that no one else can hit. And that's a pretty decent definition, but the one I really like is the one by the author of The Great American University, whose name escapes me right now, but it's a really good book talking about all the things that the American University has done for not only America, but for the world. But anyways, his definition, which he obviously borrowed from someone else, was that genius is the person that sees a target that no one else can see and then hits it. And that's what Einstein did. No one knew there was anything wrong with physics. Okay, not in the realm that Einstein fixed. We were starting to get sense of something problematic from spectra and stuff like that led to quantum mechanics, which Einstein, by the way, was in on too. But other than that, physics looked fine. I mean, most people surveyed in the late 1800s would have said, we figured it all out. All we need is to do some more experiments to make sure it's right to the 9th and 10th decimal place, as opposed to just 3 or 4. So that was what was going on. Now, what led to all this was first Newton's big synthesis of all the information of the great giants that went before him in his Principia. And then Newton also had his optics, and then we had various other experimentalists and theorists in fluid dynamics and stuff like that working. But we had electricity and magnetism put on the same foot with mechanics by a guy by the name of James Clerk Maxwell. And James Clerk Maxwell was the Lucasian Chair of Mathematics at Cambridge University, which was predominantly known as a science/math/engineering institute. And they had basically a university-wide test called the Wrangler test, every year for graduates. And it's a brutal system. It was really freaking awesome, where basically these people took over 2 days, basically 2 8-hour-long tests. And then professors graded them. And when they graded them, they then posted your score in rank from the best, which they called the Wrangler, or the first Wrangler, to the second best, which is the second Wrangler, all the way down to the last. And they just posted it on the wall. So you can imagine how embarrassing that would be, potentially, right? Unless you happen to be the Wrangler. Well, it turns out Maxwell only won second level of Wrangler on that first test. But that second test, he won the first Wrangler. So he had a little bit of this arrogance about the people around him that thought he was second best because he didn't win both Wrangler prizes. But he turned out to be a real ringer. But sadly, with electricity and magnetism, that came back to haunt him, because he actually wrote a complete treatise that was the entire science of electricity and magnetism. And no one accepted it. Everybody just sort of looked at it like, that's a crazy person and doing some stupid quaternion mathematics that no one likes, and obviously it doesn't mean anything. So, and poor Maxwell died, at a ripe old age of like 38 or something, from a horrible stomach cancer, just like his mother before him had died. So it was really a terrible scenario. But what he did when he first became the Lucasian Professor of Mathematics at Cambridge, he was a Scottish fellow. He got there and he started going through the library and stuff, and like he found the work done by Cavendish at Cavendish Laboratory, and in fact found that Cavendish had discovered Ohm's law well before Ohm had. He did it in a funny way. Basically, he would stick his arms in a situation where electricity was going across him, and he would feel pain like up to different levels of his arm height. And what he realized was that when that voltage was higher, that arm length pain was higher as well. So he really just found that voltage and current are directly related, which is exactly Ohm's law. But he did it through the pain of his whole body. And when Maxwell read that, he's great, man, I got to do this. So he builds an experimental setup, and then him and his students take turns seeing how high they can deal with the current up their arms. And in fact, a visiting professor from America comes in and sees Maxwell doing this, and Maxwell offers him to give it a try. And he was insulted. He said, I would not treat my domestic this poorly. I was really upset, but Maxwell's like, piss off. Anyways, so what Maxwell did was he went into the archives, read that stuff about Cavendish, and then he found Michael Faraday's book. And Michael Faraday is this interesting character. His father was a blacksmith, but this guy had a drive. He had some drive. He had something that made him want to be an upper level citizen. He had no hopes whatsoever of becoming, quote unquote, an upper level citizen from a financial standpoint in any stretch of the imagination. And in fact, he couldn't attend college or anything like that. So he had a sense of knowledge that you get typically from maybe a grade 16, or excuse me, a grade 12 education, grade 11 education, probably considerably better even than ours, of course, but very, very much missing some stuff. But he wanted to improve himself. So he found, get this, a self-help book. He found a self-help book that told you things to do to become a better person. And things like, there's not too many hours in the day to work. You can work a lot, 16 hours, and you're going to do better than someone who works 12 hours a day. And you should read a lot and stuff like that. So he just took this to heart, and thank God for us, because he turned out to be the man. He was an experimentalist, and he was a brilliant thinker, a brilliant logician. And he basically did every possible experiment that we could have thought of at the time, given the technology and everything. The other book he found was one called Conversations on Chemistry. I highly recommend y'all download this from Project Gutenberg. But it's Conversations on Chemistry by Miss Margaret Marcet. I believe her first name is Margaret, but her last name is definitely Marcet, M-A-R-C-E-T. And we're talking a book written in either the late 1700s or the early 1800s by a woman on science. That's a big deal. Not because women, can't do science, but because the idea back then was women couldn't do science, or they shouldn't do science or something. But she was married to a medical doctor who was intellectually curious. You know, these are post-revolution, post-Renaissance people, not unlike our founding fathers, Thomas Jefferson and James Madison and stuff like that. So they were intellectually curious, and he took every opportunity to go and see people teaching stuff. And there was this guy that she wrote about in her book that kept doing these cool demonstrations in the areas of electricity and magnetism and other types of sciences. And she wrote many conversations on this, and that was the Conversations on Chemistry. So he's learning all this cool chemistry, basic science stuff purely from this woman who's pretending to be interacting with 2 or 3 other intellectually curious women to make things reasonable, like why would you wear flannel in the winter and stuff like that. So it sort of had that ring of this is for women, but at the same time it was teaching really valuable science. Again, definitely recommend it. I've read about half of it so far, and I just love it. But either way, Maxwell did all these experiments. He did basically came up with, or excuse me, Faraday did all these experiments. He came up with, of course, Faraday's law, and he beat many people to the punch, but he didn't necessarily word it properly. And in fact, he ended up getting a job with that same chemist that was going around America and Great Britain and Europe, showing them these cool, and I'm not sure I actually went to America, come think of it, but anyways, showing off all these really cool experiments and demonstrations in chemistry. And he got a job with him, just like keeping the lab clean or something like that. And then the guy realized that Faraday was pretty smart, so he slowly started letting him do more and more until eventually Michael Faraday, became the leader of the Royal Society. And he orchestrated shows for the public, for kids, all sorts of cool stuff, where he did these shows of science for the upper class as well as for the poor people. And the only thing he lacked really was mathematics. So he was able to derive many of the same principles that other people had done, but other people put them in mathematical form. He put them in word form. And he did so thoroughly that when when Maxwell got his job, he opened up Faraday's book and could just basically translate it to mathematics. Sadly, he chose to translate it to words and the mathematics of quaternions, which was something a guy by the name of Hamilton, not that Hamilton, had invented. And it was evidently his pride and joy because he put it on his tombstone. But nobody likes quaternions. Okay, so it didn't pan out to be that good, really. It's like a 4-dimensional vector instead of 3-dimensional, and one of the dimensions is imaginary. So that's what a quaternion is. That's why they say 4, because it's 3 dimensions plus that imaginary dimension gives you 4. But anyways, he wrote it all in terms of the stuff, and nobody knew quaternions. And if you read the written word, it was even harder to get through. So a lot of people just said, I ain't messing with that crap. Ain't nothing helpful there. Well, this happened also to be right around the time Maxwell died. That was when we had invented the telegraph. And in fact, they were in the process of trying to create a transatlantic telegraph cable. Well, Maxwell dies. A guy by the name of Oliver Heaviside gets a job in telegraphy, which is this telegraph industry. In fact, he got a job because his mother, his sister, our sister-in-law, I can't remember which one, I think it was a sister, had married, I guess it has to be a sister, had married a famous physicist by the name of Wheatstone, which you'll learn about in the second semester. But through him, he got a job in the telegraphy business because the guy knew that Oliver was quite smart. Heaviside was quite smart. So Heaviside, just like Maxwell, had no background whatsoever. He was poor. His father was I don't think he was a blacksmith. He was like a bookbinder or something, but not very wealthy enough to live. They owned a house in London. That was pretty good. But Heaviside goes on and reads Maxwell's book, and it turns out Heaviside is brilliant. Heaviside, in fact, at the age of like 6 or 8 or something, took the national math test and did better than all but 2 of the students there. And those students were 16, 18, graduating from Cambridge and all sorts of places like that. So Heaviside was brilliant. Heaviside read Maxwell's book and said, this is just perfect. He's done everything. He's worked it all out. And that's Maxwell had even found things that Faraday, Volta, Ampere, Hertz, all these people had not. In fact, Maxwell had predicted the existence of electromagnetic radiation, and Hertz later found it and discovered it, and that he was right. But Maxwell had done a lot to bring those equations together, even though they got other people's names, and to actually make them internally consistent by fixing Ampere's law. So Heaviside starts reading this and is like, man, this is brilliant. And it helps him in his work. I mean, he's so good that he's this, low-level engineer and they'll find some problem with their telegraph wire that he'll say, okay, take the boat, go out to exactly 840.2 kilometers, pull the line up, and you'll find the fault right there. Like, he's that good. Okay. And he knows he's that good, and he fights for basically raises, and he keeps getting them until all of a sudden he sort of hits a brick wall where he's not getting any more raises because he doesn't have the background. And it's really kind of offensive to him. And he writes a lot of publications, and he's got some editors that are protecting him because people want him fired because he badmouths people for their idiocy. It's, you know, that guy that works with everybody who's clearly less smart than him, or at least that's what he thinks. That's what Heaviside was. He's like, my bosses are idiots. And he's like writing it in publications. But anyways, he translates and invents basically vector calculus. Him and a guy by the name of Gibbs from America both independently invent what we now call vector calculus, basically. And then he puts Maxwell's equation in that form, and that's what made it tractable. It was a group of people that historians now call the Maxwellians, which included Oliver Heaviside and a couple other people whose names escape me right now. But that was pretty brilliant. So Einstein comes along. We finally realized that Maxwell was right. His equations are dead on. You can take Maxwell's equations, as Maxwell did, and combine them in some way where they make a wave equation. And when he did that, he found out exactly what light was. He was the first person to know this is what light is, because the wave equation is a special thing where it has a second order partial derivative of something with respect to space. So d2e over dx squared is equal to 1 over the velocity squared times d2e over dt squared, so time squared. And because of that, he looked in that little slot where the V would be, and there was the permeability of free space, which is something about how easy it is to magnetize a vacuum. And there's another factor called the permittivity of free space, which is sort of about how easy it is to electrify vacuum. And when you multiply those two numbers, take their square root of the product and then flip it over, lo and behold, you get the velocity of light. You get 299,792,458 meters per second, which is, you know, at that time, as well as they knew C, that was giving them C that well. So he's like, oh crap, I know what light is. It turns out light's this electromagnetic wave pulsing in one plane, and then magnetic field pulsing in another plane, way smaller, maybe like this, but pulsing in a perpendicular plane to that. And then in a third mutually perpendicular direction is the path of travel. That's what light was. Which is amazing because Newton just finished deriving all of optics as if it were a particle, and got it exactly right, the same way we do with electricity and magnetism. But Einstein looks at these equations and keeps finding paradoxes. And this is what I mean. He's seeing a target that no one else has seen. He sees paradoxes from Maxwell's equation, because Maxwell's equations, if you convert them to a reference frame that's moving at half the speed of light, the equations don't change at all. If you move it to one moving the opposite direction at 99.9% the speed of light, the equations don't change at all. And he was getting weird paradoxes, like you couldn't see yourself in a mirror and stuff like that. And he just knew God would never create a universe in which the laws of physics were paradoxical. And in fact, everybody knows science cannot have paradoxes. Paradoxes are when two things are equally valid and predict two equally valid outcomes, but those two outcomes can't both happen. Okay, that's a paradox. If you ever have a paradox in your science sucks right then, and it needs to be fixed. Okay, so that's what Einstein saw, and no one else saw it. So he fixes it this way. He first says, okay, the laws of physics are the same for all inertial observers. This is the first principle of relativity. I suggest you memorize it. I will state it a couple more times. The laws of physics are the same for all inertial, inertial, observers. The laws of physics are the same for all inertial observers. The laws of physics are the same for all inertial observers. And what that means is whatever laws we discover, they're valid everywhere. And that ultimately leads to general relativity, which says basically all our equations have to be in covariant form. What they mean is they got to be in tensor calculus. And if you put them in tensor calculus, any coordinate transformation is going to have the exact same form. So F equals MA will always be F equals MA, that sort of thing. So that's what he's trying to do. But why did he say this weird inertial thing? Well, you can think of it in terms of Galileo's law of inertia. You can think of it in terms of Newton's first law of motion, both of which are really identical. Remember, Galileo said that objects seem to have some apparent inertia, a reluctance to change their motion. whereas Newton said an object in motion tends to stay in that state of motion unless acted upon by a net external force, or more succinctly, an object maintains constant velocity unless acted upon by a net external force. So he's saying if you ever see a frame in which there's not an obvious force acting on something, yet that thing changes its velocity, then that's a non-inertial frame. And the frame specifically he was thinking about was frames like you zoom up above the North Pole of the sun and you look back down on the sun and you don't see anything connecting the sun to Mercury, yet Mercury is not going in a straight line. Mercury is in fact being compelled to accelerate out of a straight line so that it stays in an ellipse orbiting around the sun. There's not an obvious force there, and Einstein's not willing to accept that force, that gravity might be a force. He's saying, I'm not sure that's what gravity is, to be honest with you. Okay. And Newton had a similar problem, just Newton didn't quite have the chutzpah to do all that, right? He was more excited about the things he could do right then, assuming it was a force, and he did a lot of great things that way. So Einstein says, I'm taking gravity out of the equation. So that's what special relativity means. It means without gravity. And the way he implemented that is by the non-inertial frame. Okay. Now the second principle is the absurd one. The second principle says the speed of light is a constant, independent of the motion of the source or the motion of the observer. The speed of light is a constant, independent of the motion of the source and independent of the motion of the observer. The speed of light is a constant, independent of the motion of the source or the observer. Okay, so that's like me on the back of the Mack truck when we talked about Galilean relativity. Let's say me instead of a professional pitcher, my crappy old shoulder might go 40 miles per hour or be able to throw a ball 40 miles per hour, and we're riding on the back of a flatbed Mack truck going 60. When I throw the ball in the same direction the Mack truck drives, if we suspended gravity, then that ball would go forever and that truck would go forever straight. Okay, if that's the case, we could watch it for a whole hour and we'd see a little, let's say, rust spot on the flatbed truck right below where the ball left my hand. And we could watch that for a whole hour and we'd see that ball makes a progress forward of that little rust spot by 40 miles in that single hour. And if we happen to know right below that little dust spot was a certain white pebble in the road that was so cute and we could just remember it, if we followed that rust spot moving with respect to that pebble, then we'd see over 1 hour that rust spot moved 60 miles. So the net effect is that the ball moved 60 plus 40 miles in an hour. So that's 100 miles per hour. So that's how we got relativity to begin with. Well, that's all well and good. And it's exactly right when you're talking about 100 miles per hour, 1,000 miles per hour, 10,000 miles per hour, but it goes to crap when you get close to the speed of light, depending on how many decimal places you want. So if I happen to shoot a photon torpedo, for instance, and the truck happened to be going half the speed of light, then you way up ahead of me would measure with a radar gun the torpedo coming at you at the speed of light, not one and a half, but at the speed of light. And in fact, you'd measure the truck coming at you at half the speed of light. And I, in fact, would measure the torpedo moving at the speed of light, even though I'm right behind it, moving along with it. That's the craziness of special relativity. So that constancy of light, I'm going to do real quick. We got a couple minutes. We're going to imagine a train car. And this is Einstein's Gedanken. He did all his stuff through thought experiments and saw problems other people didn't see. And he made a little light into a clock. So it's a little flashlight that pulses a flash of light. It bounces off a mirror up above and then comes back. And he called that, if you're the person sitting on the train with the clock, he called that time period delta T0, which we call the proper time. Okay, now I'm going to turn back to the document because I forgot that y'all weren't looking at the document. So here's a little train
comment on that.
What's that?
I was about to let you know. Yeah,
thank you. So yeah, this is a time period of delta T0, and it's called the proper time, which we'll get to talk about a little bit more later. And that's what you see on the train is the beam of light goes up, hits a mirror, bounces back, and then is called, and it registers 1 unit of time called delta T0. Well, to you on the bank of the railroad track, you see something different. You see the train here a little bit later, and you see it, in fact, here a little bit later. And in fact, your beam of light, according to you, does this thing. It goes up and diagonally here, and then it goes down diagonally and ends up here. Okay.
Now this train is actually moving at a velocity v. So you know this distance from here to here is basically 1/2 v times the time you measure, delta t. Okay, I'm not going to write in green much because that's clearly not very clear. So you on the bank measure a time delta t, and delta t goes from here to here. That's why I put the 1/2, because this is only half the battle, right? So this time, remember, time is just velocity or distance divided by velocity. So this would be 2d over c. But this time, delta t would be twice this distance, right? Because it's going to go up there and it's going down there by symmetry. These two are the same. And that distance happens to be square root d squared plus v delta t over 2 squared, all that divided by not c plus some fraction of v, but specifically c, because the speed of light is a constant. We just implemented Einstein's second principle of relativity. Now I'm going to square both of these, and I'm going to get 4d squared over c squared is equal to delta t0 squared. And when I square this one, I get delta t squared is equal to 4 d squared plus v squared delta t squared over 2 squared over 4, excuse me, over 4, and all that will be divided by c squared. Okay. Now, if I distribute that 4, I get, and distribute the c squared, I get 4d squared over c squared. And over here, notice that 4 is going to cancel out with a 4 down here. So I just get v over c quantity squared delta t squared. Well, this happens to be this. So I can plug that in. And when I do that, I get delta t squared is equal to delta t0 squared plus v over c squared delta t squared. Solving for delta t, I think you can easily see delta t squared is going to become, or delta t squared times 1 minus v over c quantity squared, I'll make this a square bracket, is equal to delta t0 squared. So finally we get delta t is equal to delta t0 over 1 minus v over c squared, which we often define as gamma delta t0, where gamma is defined to be 1 over the square root 1 minus v over c squared. This is a factor that's always going to be at least as big as 1, but larger. So what I would recommend you guys do over the weekend is play around with your calculator or some algebra or even a spreadsheet if you need to, but I would really prefer you do it with algebra, and find all the values of v over c that give you whole numbers like 2, 3, 4, 5, 6, 7, 8, 9, 10, 1,000, a million, 10,000, stuff like that. This is also often defined to be 1 over the square root of 1 minus beta squared, where beta is defined to be v over c. So those are some quantities we use. This is called time dilation. And what it's saying is that moving clocks appear to run slowly. This is the clock you're measuring when you're on the train with the non-moving clock relative to you. If I looked at you, I would see your second hand moving really, really slowly since you're on that train. And oddly enough, if you looked at me, you'd see that train moving, that second hand moving really slowly, because according to you, I'm moving. But the time it took, say, to melt a 5-minute ice cream is now going to be 5 minutes times this gamma factor, and that's the time you're going to measure on the side. So you're going to say, wow, he had a 5-minute ice cream and it lasted for 7.5 minutes. That's time dilation, and it just means moving clocks run slowly. So that's it. You guys are free to go. I will finish up more on relativity next time, maybe the next 2 meetings. But you are free to go, and I will wait for the last person to leave. The lab stuff is up. You guys are welcome to start that early if you want, those of you who have lab today. So I know Gavin had a question. Go for it, Gavin.
I was wondering, let me finish writing this down. One sec.
Hey, I only used one page today. This is awesome.
One complicated page that the algebra on this is really pretty straightforward. And believe it or not, this is the derivation that Einstein invented himself. It's pretty nice.
What are the two delta t's again? Like delta t is just like
Delta t
normal
is some
time
time
passing.
interval. Yeah, it's any time interval that someone not on the train sets. So it could be a second, it could be 10 seconds, it could be 20 seconds, whatever that person measures. For some event, maybe like I said,
So basically delta t is the time interval as defined by the observer, and then delta t 0 is the time interval that passes
moving
it passes
with the train.
Yeah. What was the amount of time that passes according to the person moving on the train? Or
yeah, they're linked that way. So it could be like your lifetime, like, all right, let's say you're a mosquito. If you're a mosquito on the train, your lifetime is delta t 0. But if someone's on the side of the track, they would say the mosquito's lifetime is delta t. I do a mosquito because they don't live very long.
All right. So the thing I had was, let me go ahead and share this. Can't share yet.
Oh, sorry. There you go.
All right, so this is the question. It's the rocket fired, ejects portion of its mass with the acceleration there. So from what I have written down, where is it? I did this question like a couple of different ways, I think. So what I have, all right, so what I have here is you've got force is equal to mass times acceleration, but force is also equal to change in momentum over change in time.
Right.
And the change of momentum can be defined as change in mass, is change in mass times the velocity of the gas. I guess mass of the gas times velocity of the gas. And velocity of the gas remains constant because it's just shooting out the end at one speed, predetermined speed. So you end up with force is equal to V gas is equal to change in mass over change in time. So we're going to determine the change in mass over the change in time as 1 over 160, the mass of the rocket, because it lost 160th of the mass of the rocket, divided by the change in time, which was 1 second, because it was a 1 second burn. So we've got 1 over 160. So it's basically mass of the rocket divided by 160 is delta M over delta T.
That seems, so the mass of the rocket divided by 160, that's the change in mass per time. Yeah, that's dmdt.
And the change of the duration of the time was 1 second, so it was divided by 1, so same number.
Gotcha.
So then we have delta M over delta T is mass of the rocket over 160. And then force, going back to the original, force is equal to ma, F is equal to ma. So F is equal to mass of the rocket times acceleration of the rocket.
So that's a little bit of the problem. It's really F is equal to dp dt, which is d parentheses mv. So you got to use the product rule.
What?
You got to use the product rule. P is mass times velocity.
Yeah.
So you got to go dm dt times v plus m times dv dt.
I don't know where you're going with this.
I'm not sure I'm not sure that's what you did wrong. I'm just saying.
Well, so the thing is, like,
what dp dt.
Well, so what I'm walking through my steps because these steps brought me to the right answer.
Okay.
And I was wondering, like, if there was anything wrong with it, which is kind of what you're getting at. The product rule on where exactly?
Okay, so let me show you. And can you read my notes? Is that window big enough for you to see? Right here.
I have to stop sharing 1 second.
Okay, yeah, no problem.
All right,
So
go ahead.
Newton's second law is actually, meaning this is the more correct case. It's actually d by dt of mass times velocity. That's a product. And
Okay.
calculus, we learned how to take derivatives of products. It's actually dm over dt times v plus m times dv over dt. So it's actually dm over dt times the velocity plus m times a. So that's what I was trying to point out to you. If you're having a problem, it might be because you're treating this as the truth when in fact this is the truth. This is a special case. But again, I didn't get to read the question even. I was looking for that first hint and I got fixated on that second hint. And then I looked at the question just 2 seconds ago. So I'm not sure it's going to happen. But you say you were able to get the right answer. So
I think it might be because in this case, the sum of the forces is 0 since it's in space.
Okay.
So
Yeah.
you can do change in mass over change in time times the velocity of the gas is equal to ma, I think. Well, I mean, I guess it would be equal to negative ma, but I don't really have that written down anywhere.
All right, you go ahead and share screen again so I can see what you were talking about, and open up that hint 1 too so I can see what they were talking about on that.
Oh, that's this is just a screenshot. I don't know if I can.
Oh, okay, gotcha.
I can't open that.
You're not in mastering right now?
No.
Okay, that's no problem.
But anyways, what I got to was that you kind of go back to F is equal to ma. So you've got force is equal to mass of the rocket times acceleration of the rocket is equal to what is this? Velocity of the gas times mass rocket over 160, which is what we came to. Basically, you're saying that like force is equal to ma is equal to change in momentum over change in time is equal to velocity gas times change in mass over change in time. You're like I found, like, I got all these different different ways to represent the force,
Right.
And setting them equal to each other. I came to mass rocket times acceleration rocket is equal to v gas times mass rocket over 160. So you can eliminate the mass of the rocket and you get acceleration of the rocket is equal to velocity of the gas over 160. And then you were given the acceleration of the rocket. So you multiply acceleration of the rocket by 160. So it's 160 times 14.7, which comes out to 2352 meters per second. And that's the correct answer there for 2.35. And I have this written. Well, when I was looking around for how to do this, I also ran into something that tried to do. I guess I won't really mention that because that one came out to a wrong answer anyways. But what was
this
the
is
other
chapter
one?
10, right?
Yes.
Okay.
Yeah. I'll just open up mastering 1 sec. That was so strange. I had something happen on the Pearson website, the Pearson portal or whatever, yesterday, where when I opened it up, I had access to just a huge number of courses. There was like dozens of C++ courses and stuff, and
Wow.
university physics and my programming lab for my for my C++ course, they were just buried somewhere in this. And I had probably 50 or more courses that I was signed up for, and
That's weird.
it was it was really strange, but it seems to have gone back now. So this was, I think I just completed it recently. This is chapter 9, actually.
It is chapter 9. Gotcha.
And the hint 1 was just to say that gravity is negligible in space, no air resistance, no external forces, total momentum of the system is conserved.
Gotcha. Oh yeah, it was this tutorial problem, wasn't it? That's right.
But yeah, basically I was just hoping if you could maybe walk through how you do it.
Okay, so yeah, I would use conservation of momentum just like this one's doing. What it says, a rocket is fired in deep space. It's supposed to be 1/60th of its mass is exhausted.
1/160th. Yeah.
1/160th. Yeah. So I'm looking at 1/160th dm over dt is equal to 1/160th of the mass of the rocket divided by 1 second. So it's m over 160, and that would be like in kilograms per second, say.
Oh, you know what? That might have been a thing that it was confusing me, because the bit that was kind of getting to me was that it was 160. It was 160 times the acceleration is equal to the velocity of the gas, and the units weren't matching up. We were getting 160 times meters per second squared is equal to meters per second, effectively, and so I must have forgotten the per second there.
Gotcha. Yeah, and your
Okay, so
your
that's
velocity
one
is
thing,
what,
definitely.
14.7? Is that what you said the velocity was in your problem?
Yes.
14.7 meters per second, and that's the actual acceleration. Excuse me, not the.
Yeah, that's the acceleration experienced for the 1 second that it burns and loses that 1/160th over the course of the second.
So basically what's going to happen is you've got the mass of the gas times its acceleration of the gas is got to equal the mass of the rocket, which I'll just call big M, times the acceleration of the rocket. Basically, that is conservation of momentum in this sense. You have P total is equal to a constant. And that's, of course, M gas, V gas, plus M V rocket, like that. So because of that, this is a constant. And basically what it says is the derivative of this should be equal to 0. So if you take the derivative of this with respect to time, you get mg dvg over dt plus m dvr over dt is equal to 0. And I just ignored the sign and said them equal to each other, but obviously they would go in the opposite direction. So when you put this over here, that's that. When you put this over here, that's that. So that's really what I would use to solve it. And then you just say, okay, well, the acceleration of the gas is the 14.7 meters per second every second. And the change in the gas is the 1/60th of the mass of this. So you end up getting basically the acceleration of the rocket, or they actually ask for the speed of the rocket at the end, right?
No, they asked for the velocity of the gas.
Oh, the velocity of the gas. Okay, gotcha.
I was actually kind of wondering about this. You on that equation on the left side, you've got mass of the gas. You could sub in effectively like a 1 for that, and then on the mass of the rocket, you could sub in a 160.
Yeah, absolutely.
But so is there a reason that that's a 160 instead of like a 159, since the rocket is losing that mass?
No, it's just that you're ignoring the loss of mass for the split second. In other words, you'd have to do a lot more tough calculus type calculations to take into account that, but it's going to be a second order effect. That's why he's walking you through it as a piecewise, and you're just ignoring, since it's over 1 second and 1/160th is such a small fraction. There's no need to account for the 159 as opposed to 160. So yeah, 160 would be fine. 159 is actually a little bit too much. You'd need probably somewhere between 160 and 159, and maybe it's a little closer to 159. Maybe it's a little closer to 160.
So maybe like in the midpoint ish.
Yeah.
Also, the acceleration of the gas is unknown. That's the number for acceleration of the rocket.
Oh, okay, gotcha.
Honestly, I don't know if acceleration of the gas is a given. Come to think of it, well, I mean, I guess you could find the acceleration of the gas, since it would be the only unknown at that point.
Yeah, you could actually do it at that point, because now you corrected me. This is 14.7
Yeah.
meters per second every second. So yeah, you would expect, and rightfully, you could write A gas is equal to 160 times A rocket.
Yeah, it would just be 160 times 14.7. Well, and well, so that comes out to the acceleration of, like, if that is in fact the acceleration of the gas, that is the correct number for the velocity of the gas.
Right, but that's because of V equals V0 plus AT. The initial velocity was 0 and the t is 1 second. So you're going to get exactly the same number, just just different units.
Okay. Well, so is that equation over on the right even necessary at that point, I guess?
No, you didn't use that at all. I didn't, like I said, I didn't know the full breadth of the problem, but it sounded like you were getting ready to say, well, actually F is equal to MA. And I wanted to point out, no, that's the part. That's not the true answer. This is the true answer. This is just an approximation that works on occasion. But you ended up not having to play that role at all. You could just do it from this alone. Conservation of momentum tells you this P is a constant, which means if you take the derivative, it's going to equal 0. When you take the derivative, you get mass times acceleration plus mass times acceleration equals 0, which gives you, at least within a sign, the same number, the same equation as this. So yeah, you would say 14.7 times 160. That's that 2,352 or something you got.
2352, yeah.
Yeah, 2352. And then of course, you take that and multiply it by 1 second, and that turns it to 2,352 meters per second. It's, it's a typical problem. You made it harder than it was, just by, and that's very typical, especially, with thinking people.
I mean, yeah. Well, I mean, it's mostly because I'm starting to I'm not internalizing the kinematics equations as much as I should, I guess.
Yeah, that's always that's something that's never going to go away, and you sort of should have that at your ready at all points.
Yeah, it's unfortunate.
Go through and derive them once; they'll be there forever. Use your calculus.
Right. Okay.
Or derive them 2 or 3 times. It's really pretty trivial to do it, and you can find there's a bunch of different ways to do it. You can, integrate without a limit of integration, and then you get a constant, and then you can consider initial conditions to determine what that constant is, and you'll get like V0 term come in. Or you can do it as if you're integrating from V0 to V final.
Okay. One more thing before I go. How do you what is the, I guess, in what, trying to think of the word, how to word this, in what situations are like energy is conserved versus momentum is conserved? Like I'm having a little trouble.
Okay, so
determining when to use each, sort of.
Okay, there's problems that you can solve with dynamics. You can usually solve with conservation of energy and conservation of momentum. But sometimes there's ones you really can't solve unless you use one or the other. But the deal is, those are supposed to be things that can be used as tools at any time. when you're actually on a particular homework problem or a test problem, it might specifically ask you, use conservation of energy to solve this. And sometimes that's because it's a lot easier to solve it that way than it is to do it with dynamics, you know, F equals ma being dynamics. So one, conservation of energy is always true in the purest sense. And when I say that, I mean in the sense of me writing U initial plus K initial is equal to, or excuse me, plus work in is equal to U final plus K final plus energy loss
Let's work out.
plus work out, because this is accounting for all the different ways energy can transform into other forms. So some of that energy could be wasted in doing work on an object to heat it up. Or some can be put into the system by someone applying a work to the system initially. It could also heat, you know, the friction force, it actually causes heat in the surface that it's stressing. If you can accommodate or calculate that, then you can put that as the E loss. And if it, you know, at the end runs into a spring loaded something or another, then you obviously have a workout as well. So in that sense, conservation of energy always works, as long as you take into account all the ways that energy can transform. If you have a system where it's conservative, and that's literally what the phrase is, then you have just this form. And that's always true, but only with conservative forces. And it turns out conservative forces are ones whose curl does not equal zero, or whose curl equals zero. So it turns out gravity, the electric force, the magnetic force, those are all curlless forces in some sense with the magnetism. So you can actually make scalar potentials out of them and stuff like that. Conservation of momentum, though, only works if the net external force on the object is zero, because it came from F equals delta P or dp dt. So dp dt is only zero when the P is a constant, and the dp dt can only be zero if the sum of forces is constant. So in the case of the rocket ship in outer space, there were no other bodies acting on it. The force of the particles of gas exploding and pushing the rocket forward was a force of one part of the system on another part of the system. So those are all internal forces. That's why the net force was zero. And then, of course, you have elastic collisions, which is only true when kinetic energy is conserved. And that's a very, very rare situation. But at the microscopic and, you know, atomic scales, it's common. Does that make sense?
Yeah.
But yeah, a lot of it,
I was just kind of wondering about if there was like a guideline to follow, but yeah, just kind of use whatever, you know, needs to be used at the time, basically, right?
Yeah, if you're on a chapter on momentum, they're probably wanting you to use momentum methods unless they
more than likely, yeah.
Yeah, so that's the big thing. But the weird, and this is sort of weird, but it's more like your math class. At any chapter, we expect you to have everything before it mastered. So you're getting into relativity now. That means I expect you to know all of chapters 1 through 10. And in fact, your textbook author sort of pretends like he expects you to know all of chapters 1 through 35. Because I think 36 is the chapter on relativity. Hopefully I remember that correctly. But I labeled it on my paper anyways.
Might be a little rough, but we'll see what we can do, I guess.
Yeah. But yeah, that's the nature of science and math. They sort of assume you know everything that came before, even though you often have to look it up.
Yeah.
Brandon, did you have a question? I assumed you guys were probably just sitting here, didn't even know, didn't really even know you were still logged in or something. But if I want to make sure I give you a chance if you have a question. I was getting ready to do Taylor as well, but he's gone. No. Anything else, Gavin? Then
might have just been following along, or forgot to turn it off.
Well, anything else, Gavin?
No, I think that's everything. Thank you.
You already had lab this week, haven't you?
Yeah. Lab was Wednesday.
Okay, that's cool. I was just making sure, because I told everybody I opened up the module early for the lab today in case anybody want to start early. It's not that hard of a lab, I don't believe.
Actually, let me you know, while we're on that subject, let me take a look at it. What is it? Lab 8, nonlinear 2.
Yeah.
Let's see. Yeah, just looking at the weird units and stuff like seconds squared per meter.
Yeah, per meter to the 1/2 power or something weird like that.
Oh, so on the equation, when we put the A1 is 2 and we're applying it to time, so for the equation, normally it would have been time is equal to a number times distance, whatever the whole equation is. Would we put time to the power of 2 since we're raising time
Yeah,
to the A1?
yeah, your y equals mx plus b would be t squared equals m times d plus b.
Okay.
Yeah.
So I was wondering about that. So I guess I was doing that right. I will say I had trouble. I mean, it's on the previous week's lab, so it's already turned in and everything. But I had trouble, I guess, graphing the different A1s. Let me see if I can show you. It ended up looking really funky, and I'm not sure if it was what you were looking for, but
Yeah, the
I
sizes
did what I
are so
could.
drastically different, so they didn't come out quite as nice. But I just wanted you to be able to do that graph or several graphs on one page. That was sort of the whole purpose of me doing that.
Yeah, here it is. This is
Yeah.
what that graph ended up looking like.
Yep. Yep. That's about right.
Oh, that is actually what you were expecting?
Yeah. In fact, I did it myself and got the same sort of look. You end
Oh,
up having
okay.
such a large range in one data set than you do to another data set that some of the data ends up in the left eighth of the page.
Maybe I should have gone with like a negative 0.25 or something, because then it would have come into a nice sort of like ocean wave kind of look thing.
Right. Or you could, multiply each of the values by 100 just to make the scales approximately the same. Or, the biggest blue dot seems to be about 1, whereas the biggest yellow dot seems to be about 5. So if you multiply the X data for the blue data, if you multiply the blue X data by 5, you would get it spread out over the same range, and you just make that adjustment there. So you can do all sorts of neat stuff to make it look more reasonable. But yeah, I did expect it to look like that.
Okay.
Right.
All right. Thanks for your help.
All right. See you guys.
Enjoy
Have
your
a good
weekend.
one. You too. See you, Brandon.